All right. Hi, everybody. Hope everybody's having a good week so far. Um, can somebody just give me a thumbs up on the participant list if they can hear me okay? And the visuals are working good? Okay, perfect. Thank you so much, guys. So the game plan today is to introduce the concept of current to touch on start chapter 27. And we're going to be working on this chapter all week long. It's a pretty short chapter, actually, so we might be through the bulk of the material by the end of the day tomorrow. And then if we have extra time, we can use Friday to answer last questions or take pending or sort of take requests and see what you guys want to cover. Thank you guys for completing your homeworks last night. I saw a bunch of the written homeworks come in. I haven't had a chance to look at those. It's going to take me a while to get through those. I've got 70 of them to review and grade. So probably at least a week until I get the final stack graded. Okay, good. Are there any questions before we get started today? All right, great. So to start off today, I want to do a few demonstrations to try to motivate the idea of electrical current. So I'm going to temporarily stop my video and rearrange my setup here, my camera. Okay. Okay, great. Uh-oh, I'm gonna turn that off too. Okay, great. So this chapter is about electrical current. And so I guess to get started, we just want to get a physical intuition for what we mean by electrical current. So when I ask you guys that, so let's try to have a little bit of a discussion today. What is an electric current? When I say that, what is a current? What do we mean when I say an electric current? What do you guys think about? Anybody want to?
I think of like the flow of electrons, from the positive end to the negative end. That's like what kind of comes to my head first.
Okay, right. That's the exact right idea, right? The flow of electrons around in some sort of a circuit, right? So there's a lot to unpack there, right? So here we have a setup. We're gonna play with this little thing, right? Right here I've got a battery, right? So this is, we talked about those last time. This is what we're thinking about batteries as they're little portable voltage sources, right? So there's a positive side to this battery and there's a negative side. There's two metal plates separated by some distance that have excess charge built up on them. One side has extra positive charge, one has extra negative charge. And then I've connected those to each side. So underneath this is one plate and it's going to make contact with this piece of metal here. And then I have a conductor that I've laid over the top, right? And we know that when I connect two pieces of conductor, then they're going to all be at a common voltage, right? So here's my 3-volt source. Now all the positive charges that were built up on this battery, because they're in physical contact with this conductor, they spread out in this entire piece of conductors becoming positively charged. Right on the underside of that thing, right, there's physical contact with this contiguous piece of conductor. It's all at a common voltage and those negative charges, excess negative charges are spreading out over this surface. Okay. So what's the voltage difference between this piece of conductor and this piece of the conductor, right? This gap that I have here in these two wires, what's the voltage difference across that gap?
3 volts.
Yeah, it's going to match the battery, right? We talked about that last week. It's got to be 3 volts because this piece of conductor is at the same voltage as the positive terminal of the battery. This piece of conductor is at the same voltage as the negative battery. So that means they're going to share the voltage with the battery. So there's 3 volts across that. And right at the moment, there's no path for these currents, for these excess charges to flow. But what we know is that if I were imagined to take another wire, so if I bring in some piece of conductor, and I were to complete this circuit, right, touch these 2 sides together, okay? Well, now I would have a situation where I have a contiguous piece of conductor, okay? A continuous piece of conductor. And that means that the excess charges could try to flow, right? If I have, say I have free electrons that are able to move through this conductor, that they could flow and try to return to the positive side of the battery. When I have that set up, if I were to make a continuous circuit here and connect this, so I just have a, sort of a single piece of conductor that goes from the negative side of the battery and returns to the positive side of the battery, is that piece of conductor going to be at a constant voltage? What do people think? People are giving thumbs up. Well, let's think about it. Our idea is that if we connect this, then some current will start to flow. Would current flow in the case where the entire setup, the entire circuit, would current flow through that if it was all at one potential?
No.
No, it won't, right? Remember what we said last time is that changes in potential lead to electric fields, and electric fields are what push charged particles along, right? That was the connection we tried to make last week. So the only way that the charges can flow through this is if there's a variation in the electric potential through that wire. And that comes about in this case because the battery is this special device that can keep loading extra negative charges onto this thing, right? So the battery keeps pumping extra electrons onto that negative terminal, keeping it at a low voltage, right? And pumping them through this circuit, and they return to the positive side. And for every positive electron that gets back, or every electron that gets to that positive terminal, the battery pumps another one out onto the other side until at some point the battery becomes completely depleted. And then this thing will eventually reach equilibrium, right? Eventually all the free electrons will distribute themselves in some uniform way. And then I'll have static equilibrium. Then the thing will just sit there and there'll be a constant voltage across this conductor. So while all that is happening, this is a non-static equilibrium situation. There's going to be a voltage gradient that gets set up here that varies this thing by, say if it started at 0 volts on the negative side here, that voltage would vary until it gets to positive 3 volts on the other side of the battery. And that sets up this dynamics, right? So then I have a varying, right, a gradient of the electric potential through this thing that's going to generate an electric field. We know if there's a changing voltage, that means there's going to be an electric field, and that electric field is going to point along the direction of the wire and push those charged particles through the wire. So this is an inherently different kind of system than we studied in the last chapters, when we were really thinking about things that were in electrostatic equilibrium. Circuits are a completely different situation. They're dynamic systems that are moving. And so once I have a full circuit, right, I don't have that all the various conductors have to be at a constant voltage. In fact, I can't have that. I end up with a gradient of voltage across the thing. So just keep that in mind, that when you have charged particles that are moving and they're dynamic, all of the things that we established about electrostatic equilibrium don't hold anymore. So we have this way of setting up moving charged particles. What are the ingredients? We need some sort of a potential difference, and we need a gradation in that potential difference through our conductor to generate an electric field that's going to push the free charges. Okay. Once we have that, we can try to push, right? We can try to visualize the dynamics of this, right? So a very common thing that we might do with a circuit is try to light up a light bulb. So right now I have a little LED here that I can connect across the terminals that I have here, and you can see it lights up red when I complete this circuit. That's already showing us that this is a very dynamic system, right? the state of this light bulb makes dramatic changes when I go from it not completing the circuit to completing the circuit, right? I see it light up. What is light? Light is you can think about it like it's generating some heat. It starts generating some extra photons. Something happens, right? There's things being produced. Its state is changing. So that's an indication that there is something dynamic happening, right? Something is starting to move because the system is changing. And the thing that is moving around are those electrons. They're being pushed through this potential gradient in the wires through this little device. And the way the device happens to work is it excites, right? When those electrons come through, they excite other electrons into special states that when they fall back down, generate light of specific wavelengths. So we can see just from lighting up a light bulb, if we think about it carefully, it already implies that there has to be some sort of particle, that's moving around, there has to be some sort of dynamics in the system. Let's see a few other examples of that. So I can do something like this. So here's just another battery. I've got a 1.5 volt C-cell battery. And I'm going to bring a compass nearby it. Okay, so here's a compass. It's pointing north. And what I can do is I can take and I can complete the circuit. So again, I've got a positive side and a negative side to this. And all I'm going to do is connect the two terminals of this battery together. And let's see what happens to that compass needle. When I connect those, you can see the compass needle jumped. Goes from being at rest to, oops. Right, you can see it starts jumping around when right, I'm not touching the compass. You can see it starts swaying around when all I'm doing is breaking and completing the circuit and I can get that thing moving. That's really interesting. That's another indication that there's some dynamics happening here. This is even more obvious than the light bulb, right? I have a physical object, this compass needle, and it starts deflecting, it starts moving around. So there's a change in the momentum that you can visibly see with your eye. We know that if those particles, those mass particles and those needles are moving, that there's a conservation of momentum back on the other side, right? Back on the battery side in the loop, there have to be particles that are now moving around that are also experiencing the equal and opposite reaction that's leading to the change in momentum of the needle. So there have to be small physical objects that are moving around inside of that wire and somehow transferring momentum over to that needle system. And that's all happening. We know now from careful study of over hundreds of years that those are the tiny electrons that are mobile inside of the conductor. One more quick example we can do here, or maybe two more examples. Here's another battery, another C-cell battery. And now what I have here is a wire. Okay, just a piece of copper that I have shaped in this specific shape. And what I'm going to do is I'm going to put this wire over this battery and let it make physical contact with the positive and negative sides. And notice what happens. This thing starts spinning. Okay. So here's another example. I can see some real physical motion. I see that mass of that wire is starting to spin around as it sits here. And that's because there's current flowing through this thing. And not only current, but on the bottom side, the thing that's making this thing drive is I have a stack of rare earth magnets sitting here. Just like that compass needle, it was a magnetized piece of metal. So somehow electric currents, when they come near magnetized objects, can transfer some momentum over to that system and things can push and pull. So this is showing the other example, right? That I saw that compass needle deflect. In this case, I can see that the other side, that this charge flowing through this wire is also experiencing the momentum. Right now, that current that's flowing through that thing is getting pushed, right? That's the counter momentum, right? The equal and opposite force. The magnet system side of the system is getting pushed, but also the particles inside the wire, those little flowing electrons are getting pushed, and there's some real dynamics in this system. Yeah, Manuel's asking if, yeah, so this is a very crude, right, electric motor, right? I mean, we're going to study motors a little bit. This is about the simplest one you can make. All you need to make a motor is a magnet and some current, and you can make a motor, right? You guys can build that thing at home. You just need to stick a magnet on the bottom of a battery, bend a little wire so that it kind of makes that balanced loop, and it'll spin around on that axis like that. It's a pretty cool trick. Okay. One other thing, and then we're going to jump into the slides here. Let me bring back my little circuit here. And let's bring out this device here. So what do I have here? I've got two light bulbs, and now they're attached end to end. We're going to call this batteries hooked in series. Remember, we introduced this idea with capacitors. Electrical components that are hooked end to end, we say, are hooked together in series. What do we think? When I connect this pair of light bulbs to this circuit, what's going to happen to the light bulbs? Well, they're going to light up, but here's what I want you to think about. Which one is going to be brighter? The one near the positive terminal or the one near the negative terminal, or will they both light up with the same brightness? What do you guys think?
The positive terminal should light up a little more, no?
What do people think? Why would that be? Why do you think the positive one is going to light up brighter? Let's get a few more ideas.
Well, actually, wait, for series, yeah, don't series bulbs actually tend to get dimmer as they go along?
Okay.
Oh, wait, no, yeah, they have the same current because they're in series, so yeah, they should be the same brightness.
So yeah, let's think about this. The current, right, these electrons that are flowing through this thing, right? I have physical electrons getting pushed along here, right? So if I have one electron that gets pushed through this battery, right, then I have to have another electron come out the other side. Why is that? Otherwise, I would get a buildup of electrons, right? Imagine if I had more electrons flowing in this side of the light bulb than I did on this side. Then somehow this, right, this center part of this thing or this object would start filling up with an excess of electrons. Okay, and we don't observe that. What we observe is that electric gradient, right, because I have a fixed voltage source, stays the same. And so for every electron that comes into this thing, an electron leaves it. There's a conservation of electrons flowing through this circuit. There's a current conservation here. And so the number of electrons that flow through this light bulb has to be the same number as the number of electrons that flow through this light bulb. So if you just isolated them independently, you would have this kind of device with a certain number of electrons per second flowing through it, and you would have the same thing on this side. So you wouldn't be able to tell if you, in isolation, the difference between those two batteries. And so the idea is that they should light up the same, okay? And I don't know if you can see that. They're very dim, but they light up to the same brightness. Can people see them lighting up? They're glowing kind of orange there. Okay. So current, this is another idea we're going to focus on. Current is conserved around in a circuit. If I have a certain number of electrons that leave one side of the battery, the same number of electrons have to return. Otherwise, I would get electrons filling up in some portion of the circuit, and I don't get that. We're going to see that it's a very good analogy if you have trouble wrapping your head around what's happening with the electrons in the circuit, to try to think about what would happen for water flowing through hoses or pipes. It's the same idea. The electrons are physical objects that push around on each other and have to make their way through this conductor, just like water is a physical object that has to make its way through the hoses, right? So if I had a garden hose and it was completely full to start, and I pushed some water into one side, say I pushed an extra cup of water into one side of the garden hose, and it was already completely full, well, then an extra cup of water would have to come out the far side because there has to be some sort of conservation, right? The hose can only hold so much water. The same thing's happening here. Remember, our model for a conductor is it's a material that's just filled up with excess charges. So it's exactly like that water hose that's filled up with water molecules. It's a material that's just filled with free electrons. And so if any extra come off of a battery, it just will push those extra electrons down the circuit, and we get this conservation of current idea. Okay, let me stop my video and jump back into looking at you guys mode. Okay, great. Are there any questions about those demos? The whole idea there is just to motivate the idea that current really is, right, some dynamics, some objects that are getting pushed through those conductors. And there are real physical implications, right? They can, that current, those objects that are moving around can turn into motors, right? Things that push physical objects around. They can generate magnetic fields that we're going to see later. They can light up light bulbs. All sorts of interesting dynamic things can happen once I have current flowing around in a system. Okay. All right, let's go ahead and jump into the slides for today then, if there are no questions about the demos. Sorry guys, my Zoom is not wanting to connect to my iPad for some reason. Aha, there we go. Okay, so let's jump into the slides that I brought today. So we talked about this just now in words, right? But this is the model for, right, the idea of electric current. This is the model we're going to have. That we know that inside of a conductor, we have these free electrons and we have these heavier fixed positive objects. And they're flowing around, right? And these electrons, right, if there's an electric field indicated by that pink line, those objects are going to try to move against that electric field, but they may encounter or bounce off of these positive charges. But in total, in sort of on average, they're going to make their way through this sort of mesh of positive objects. So there's a velocity, right? If I have an electric field, it starts pushing those electrons to the right, they're going to gain some average velocity. Now they won't just accelerate forever because they're going to encounter these positive cores of the atoms inside of the material, and that's going to slow them down from time to time. But in these empty spaces between the positive charges, they're able to gain some speed, and so there'll be some average velocity that they drift with to the right. So in order to create a current, so that velocity, right, we could think about how would we calculate that drift speed. Well, if there was some average velocity that the electrons were moving to the right with, then we could end up with an expression like this, right? It says that the drift velocity, well, let's rewrite the drift velocity in terms of something we talked about in Physics 313. Well, if there's a velocity, imagine that the electrons start from rest, okay? Well, then there's going to be in order for them to reach some average drift velocity, there has to be an acceleration acting on them for some duration of time t. Okay. What would be generating that acceleration? Well, it would be some force, right? A force divided by a mass would be an acceleration acting over some time t. And we're talking about some charged particles. So what is that force? That force has to be the charge times some electric field divided by the mass of the particles times time. And if we're talking about electrons, then we can write down particularly that this drift speed has to be something like the charge of the electron times the electric field that they're in divided by the mass of the electron times this tau, right, constant, which is like the typical time, mean time, the average time between collisions. That's the average amount of time that they accelerate before they bang into something and momentarily stop and then have to get going again. So that's the idea of this drift velocity, that the electrons aren't just free to just completely make their way through the conductor, but on average, they have some drift speed that they move in the electric field with. And so we can also then define something that we call the electron current. So if we imagine that we have a bunch of electrons, okay, and they're all making their way in some space to the right with this average drift velocity, well, we can try to count the number of electrons that pass through some area per second. So if I imagine just making a window that has some cross-sectional A, and I ask, what is the question, right? What is the number of electrons that pass through my window per second? And that's what we're going to call IE, the electron current. It tells me how many electrons pass through my window per second. And to calculate that, turns out all I need to do is have these physical quantities. I need to know NE. What is this? This is the electron density. This is the electrons per volume inside of my conductor, or in my space, right? How many electrons per volume I have that are flying along. And then if I multiply that by the drift velocity, okay, and the cross-sectional area, right? Because the number of electrons that pass through that cross-sectional area, you can imagine if I had a bigger window, I would get more electrons per second passing through the bigger window than the smaller window. So it scales proportionally with the area of this answer. Let's check out the units on this thing. This thing, the electron density, has units like electrons per cubic meter. A velocity has units, what, like meters per second. And it cross-sectional area and area has units like meters squared. So you can see all the meter units cancel out of this, and this thing has units like electrons per second. This is another measure of how many electrons per second pass through that cross-sectional area. All right, great. So here's a quick question. We're talking about an electron current here. Is that the only kind of a current I can have? Electron current? What do people think?
Can't you have proton current too, technically?
Photon current?
Proton.
Proton current? Hold on, let me turn my volume up a second. Proton current? Sure,
Yeah.
how would you have proton current? Well, right, I would have to set up, just generically, all I would need is some protons. They're positively charged objects. If I just had a collection of free protons, and I put an electric field around those protons, right, something like this, put them in an electric field, okay? They're gonna start drifting with that electric field. They're gonna experience a force and they're gonna move forward. They're gonna have some velocity, right? They're gonna start accelerating and gain some velocity in this direction. And then all the same things, right? I could also define a current that would just be the proton current that counts the number of protons that pass through some cross-sectional area A. Okay, So this idea of a current counting things, right? I can have a positive, right? How would I get that? Well, that wouldn't happen in a typical like metal conductor, because in that setup the electrons are free and the positive charges tend to be held in sort of this lattice. Okay. But you can do things like take a hydrogen. So a hydrogen atom is a proton with an electron orbiting around it. And if you expose that hydrogen to the right environment, you can strip away that electron. You could have a big batch of hydrogen, ionize it to get rid of that electron, and end up with basically a bottle of protons. And then if you take that bottle of protons and you put it in an electric field, they're going to start moving, and you can get a proton current. This is exactly how particle accelerators work. The kind of particle accelerators where people study fundamental particle interactions are also particle accelerators that are used for like cancer therapies and things like that at at hospitals and various places. What other kind of objects can create a current? Well, really with this definition, right, of electron current, proton current, right, I can define a current for kind of any physical object that I just count the number of particles that flow through that object. It's almost like that idea of a flux that we had before, right? So I could even have photon current, right? I could have neutral light particles all cruising along here. And if I defined some cross-sectional area, I could count the number of photons that pass through that area. I could have, say, heavy ions, right? Maybe I have 2 protons and 2 neutrons stuck together in an atom that I've ionized, right? So there's only 1 electron, so I end up with a net positive ion. I could have a bunch of ions all moving in some direction under the influence of an electric field and generate a current. In your homework example, we talked about this lightning, right? And the way I had it set up was that I had positive charges. A lot of people that, I had a few of you email me about this, right? The way we had it set up was that the cloud was positive and the ground was negative, and we wanted to think about the lightning coming down from the cloud. Well, in that setup, the way that lightning would have to be produced is that it would be a lightning bolt of some positive ions flowing down towards the ground. And that happens in real life. You can get different versions of the charged particles that are established in the cloud and on the ground flowing between the 2 parts of the system. So current, what I don't want you guys to do is get stuck in your head that an electrical current can only come from electrons flowing in, conductors. Any charged particle, any object that can have an excess charge, I can accelerate it in an electric field and generate a current. We're very typically going to be focusing on electrons being accelerated by potential differences in a conductor, and so the free charges will be the electrons. That's going to be our typical example, but just remember that the other kinds of things exist, the other types of currents exist. All right, we already talked about this, right? The idea that current is generated by this sort of non-equilibrium system. I have excess positive charge on some, so how do I get these electrons flowing in a wire? Well, I have some cross section for a wire. I put an excess of positive charge on one end of the wire, negative on the other side. That generates a potential difference or an electric field, and then that's going to push the free electrons in one direction. Now we're going to define another quantity that we're going to call the electric current, or just the current. When we say the current, it's going to be I. And I is going to always point by convention, just a choice, that the current is going to flow from the positive side of our terminal to the negative side of our terminal. This is a little bit of a weird historical kind of quirk in the way we describe electrical systems, because we understood that there were charges flowing in these systems by looking at the dynamics that unfold when you create circuits like we did in some of our examples, before we really understood that it was the free electrons that were moving. And we established early on that the electrical current flows in the direction of positive to negative, before we learned that it came from the electrons that are actually being pushed in the opposite direction. Okay, so that's a weird kind of convention quirk, but it's one that we live with for historical reasons. So then what is the conventional current I? Well, we just talked about the electron current. And then I could just define the conventional current in this way. The conventional current is just the charge of that particle that's flowing times the number of electrons per second that pass through those things. If I unpack that, right, this is like the charge, right? Let's look at this. This thing I is like the charge of the electron times the current of the electron. This is the charge times the number of electrons divided by the time. Well, this is a charge times the number of electrons. That's like the total charge that flows through that cross-sectional area that I'm investigating in a fixed unit of time. So that leads to our more generic definition of the current. It tells me the amount of charge that flows across some position in a current carrying wire in some amount of time, delta t. So in order to think about the regular current, what I would do is imagine sitting at, right, if there was a wire and there was some charge flowing through this thing, what I would do is imagine sitting at a certain point and I would count, right? I would try to find the total charge. So I would just sum up all the charge that flows past that particular boundary in some amount of time, right? I would say, record how much charge flows past that position in 5 seconds, and I would take the ratio to establish the electric current. One last definition is the current density that gets introduced in this chapter. We said that we always calculate the current flowing through some cross-sectional area. Well, I can take the ratio of the current to that cross-sectional area to get the current density. Okay, that's going to be how much current per cross-sectional area flows through this wire. We said that when we have these currents, right, they're physical objects generating the current, and we're thinking about wires being like full of electrons. So if I push an extra electron in one side, that extra electron has to come out the other side. If there was a split, right, a divergent, a point where the electron could choose to go one way or another, if I put 10 extra electrons in this side of this conductor, what I would have to get is that on this output side that I would get, right, 10 electrons coming out here. Maybe I would get 5 and 5, or maybe I would get 4 and 6, but all those same number of electrons have to come out of the other side. Just like for a water hose again, right? If I had a hose full of water and I push, say, a gallon of water in this side, and then there's a place where the hose divides up, well, that gallon of water has to divide itself down those two branches evenly so that a gallon of water comes out the far end of the hose. And the same thing holds for electrical currents. Okay. We write this down as Kirchhoff's junction law. It says all the input current, all the currents flowing into some junction have to be equal to all of the current electrical currents flowing out of that junction. And we're going to see how that looks as we go along today. Okay. So that's a real quick overview of the concepts that were introduced in this chapter. So let's do some quick check problems to see how we're doing with our understanding. So first one, if I have wire that's carrying a current and two different wires, if I have wire carries a current, if both the wire diameter and the electron drift speed are doubled, what happens to the electron current? How much does it increase by? Let's go ahead and launch the poll. So I imagine I have a wire and then I double the diameter and the drift speed. What does that do to the electron current? Okay, I still have answers coming in. I'm going to give you 5 more seconds to Record your response. Okay, let's go ahead and end the poll. So we have a split between a factor of 4 and a factor of 8. Okay. Well, let's remember here, the electron current, what was the formula? That it depended on the drift velocity and what else? And the cross-sectional area A. Remember, we can flip back to our definition here. Okay. It depended on the density of the electrons, the cross-sectional area A, and that drift velocity. Well, this thing goes up by a factor of 2. How much does the cross-sectional area increase by? Well, it says that I double the diameter of the wire. Okay. Well, the cross-sectional area is going to be something like pi times the diameter over 2 squared. So if the diameter doubles, then the area goes up by a factor of 4. 2 times 4 gives me a factor of 8 increase in the electron current. Depends on the area and the speed, right? If the electrons are moving along really rapidly, right, the faster they're moving, the more can get past that little cross-sectional area in a given amount of time. So it depends on their speed and the cross-sectional area A. What about this one? I have a wire and it has this gradient of positive charges set up like this, so it's more positive on the left than on the right. What direction would the free electrons in this conductor move? Oops. Sorry, let me relaunch the poll. What direction would those free electrons move? I'm going to go ahead and end the poll. Okay. The answer here is they're going to drift to the left. Right? The electric field is going to point from positive to the negative end of this terminal. That means a negative charge here, right, is going to experience a force. The force acting on that thing is going to be like the charge minus the fundamental charge times the electric field. So this guy is going to experience a force back against the electric field, and it's going to be pushed to the left. So the electrons are flowing towards the more positive. They want to make their way down to the more positively charged side of this thing. What about this guy? For every minute, I'm looking at a fixed position on a wire, and I see 220 coulombs of charge flow through that cross section. What's the current flowing in the wire? Okay. Most of you selected D. Okay. Remember, our definition for current is charge that flows past that cross-sectional area in a fixed amount of time. Well, we said we look for 60 seconds, 1 minute, and we saw 120 coulombs of charge, okay, flow through this wire. So that gives me something that's like 2 amps, okay? So amps are our units of current. What is an amp? An amp is a coulomb per second. Tells us the amount of charge that flows by some area in a given second, okay? That collection of standard units we call an amp, okay, or an ampere. All right, what about this one? Can you calculate the current density for this wire? Remember, our definition of current density was the total current divided by the cross-sectional area A. Okay, I'm going to go ahead and stop the poll. Okay, we had some split between B and D for the responses. We didn't get many responses here, so let's see what happens here. We see that there's 8 amps of current flowing through this wire. Remember, the current is constant, so everywhere in this wire there's 8 amps flowing. Okay. What's the current density going to be? Well, I have to divide that by the cross-sectional area, which is 2 times 10 to the minus 3 times 2 times 10 to the minus 3. So this is like 8 divided by 4 times 10 to the minus 6. So this has to be like 2 times 10 to the 6th amps per square meter. All right, what about this one? Let's see if you remember what I said earlier about this guy. I have 2 batteries hooked up in series to a light bulb. Which one is brighter, or are they the same? I'm going to give you guys 15 seconds on this one because we already discussed this. Okay. Okay, almost all of you are picking C, that the bulbs have equal brightness, and that's absolutely right, right? If they're identical light bulbs and there's current conservation, I know that the current flowing in this portion of the circuit has to match the current flowing in this portion of the circuit, has to match it here because there's only one path for those electrons to take. And so that means that this is a battery with current I flowing through it, or it's a light bulb. This is also a battery with current I flowing through it. And so they're going to light up identically, right? They look like physical objects, the same physical object with the same number of electrons flowing through them in a fixed amount of time. So they have the same physical response and light up with the same brightness. Okay, so I'll post this website on Blackboard in the announcement after class here. That's the last problem I wanted to look at, but I just wanted to also point you guys, there are lots of different tools like this on the internet. So that are little circuit simulators. This is one that's pretty simple and easy to play with at this falstad.com/circuits website. And so here you can see I just set up a little simulator of this exact circuit that we were looking at just a second ago. So it's 2 light bulbs that are hooked in series to a battery. And so you get this visualization of what might happen. So these are both like 100-watt light bulbs. Okay? And there's some 5-volt source over here. And you can see what happens is I get these electrons, right? You can imagine these electrons are flowing around with a constant circuit. You can see that every electron that makes its way past some point has to flow through the battery and eventually get down to the other side. And the little simulator, right, I could calculate, we're going to see later or tomorrow when we look at Ohm's law, we can calculate what that current has to be. And typical currents flowing around in a circuit are usually something like a few hundred, right? So what is this? This is like 0.2 amps, right? So amps are a good unit because they also tend to correspond, right, at the scale of currents that flow around in typical types of circuits. So amps are a good set of units because in traditional circuits, we have amp level amounts of current that are flowing around. So I just would urge you guys to get on this, and if you're having problems visualizing what's happening in a specific circuit, try one of these circuit simulators, and I'll be showing these from time to time in class as we talk about circuits. Play around with them, set up the circuits that are being shown to you, and see if that doesn't help you kind of wrap your head around what's happening. Okay, we're going to stop here for today. We're going to just pick up right where we're leaving off tomorrow and introduce or keep talking about some concepts of current, and then introduce Ohm's law, where we can try to understand the relationship between resistance, voltage, and current. Okay, that's it for today, guys. Thank you so much. You're welcome to take off now. I'll hang around for any last questions if there are any. Have a great day. I'll see you guys tomorrow. Bye-bye now.